All right. Looks like it's going. Let's, can I see the whole whiteboard on this? Yeah, I can. Don't let me cross this line before moving the camera. And let's continue where we left off last time. Well, first let's do a recap of the last stuff that we did last time. Jeez, 4 of you.
Dying down.
Yeah, it dies down quick. I usually expect to keep about 1/3 to 1/4 the students I start with.
Wow.
When it's a class like this.
That's sad.
Yeah, Jacob. Remember geometry?
I'm pumped about this one.
That's good.
I'm going to be honest.
We might go back and do geometry. You would have loved it.
Yeah, I was just in the middle of dirty work. So I was just a degenerate.
Alright. So first off, one important thing that we covered last time that's going to come up 100 times, so let's make sure we understood it, is called the union lemma. So this was the only major proof we did last time, I think, other than our set theory proofs. So let X be a set and let C be a collection of subsets of X. So we got subset X and now we got a collection of subsets on X. And we're calling that C. If for every element in big X, for every little x in big X, there exists a subset in C such that X is in that subset, then the union of those subsets is the set X. So if I have a set of subsets, and for every point in X, it's in one of those subsets, then the union of all those subsets is just a set X. If that sounds very obvious, it should. Why we had to prove it, a lot of it was just to give you the notation. But I promise you that there's going to be points in the proof where I go from one step to the next, and you're going to say, how'd you do that? I'm going to say, remember this? So, very useful lemma, again, come up 100 times. So do we have any questions about this? Anything we need to review, or do you think you got it?
I think we're good.
Why do you call it a lemma? Like, the way I think of lemma is it follows from a proposition, but...
No, that's a corollary. So, we come up with a bunch of fancy words that all really mean just a theorem. So we say lemma, corollary, and theorem. They're all just theorems, they're all just proofs. There is no difference between them. As a general rule, we use lemma if it's a small proof to help us with a bigger proof. And as a general rule, we use corollary if it immediately follows from a proof.
Oh, okay.
So that's just terminology, but they're all just theorems. You could always just call it theorem. I'm just following the naming of the book. I assume none of you actually have the book, so maybe it doesn't matter.
Mine came in today.
Oh, you got one?
Barely.
I want one.
Go get one.
What is it called? Oh yeah, first.
Lecture 1, right at the start. I have it written on it. It's in the view of the camera. You don't even have to play it.
What was the price?
It was like, what, $20?
Did you get a
Not
hard
that
copy and
expensive.
everything?
Nah, Big Words
something.
site is useful though.
Yeah. So I mentioned a way to get it. There's a website called bigwords.com, which is a mailman website for getting college textbooks. Always use it. Sometimes you can find like some international version printed in India for like $5, including shipping. It costs 50 cents and then $5 to ship it.
Well, you don't want it in India. You want it.
No, it will be English.
Oh, the English.
Yeah.
I see.
So
Is that it right there?
yeah, that's mine. You can take it if you want. We're on chapter 0 still. Okay, so that's the union lemma. Did we have any other questions about union lemma? All right, and then we had some basic new definitions. A minus B, I think we're all good with this. It's the set of everything that's in A and not in B. A minus B. The more important one was A cross B. A cross B is a set of all ordered pairs x, y, where x comes from A and y comes from B. We good with that one?
Yeah.
Okay. And then we had this more generic notation. If I have A1 cross A2 cross blah 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 cross AN, that's the set of all n tuples, where the first thing came from A1, the second thing came from A2, etc. The last thing came from AN. Make sense?
Just the same thing.
Just the same thing, just we're crossing together more sets. And then for any sets A, B, and C, we had these 7 theorems of set theory. Now in topology, as we're going through topology, the majority of the time we're dealing with sets directly. So these basic theorems on sets become very useful in things that are referenced more than they are in something like discrete math or calculus. So let's make sure that we understood all these, try and at least get some intuition for how they work. We did a bunch of proofs of them last time, so you can go rewatch those proofs if you want to see proofs of them, but let's just try and get intuition. So everything that's in A and B or C is everything that's in A and B, or it's in A and C. Sound good? You like it? Still need to think about it? Should we draw some pictures?
No, that worked.
That worked? Okay. Now, everything in A or B and C is everything that's in A or B and A or C. Is that one clicking with your intuition?
No, but
No?
Pictures would help for sure.
Yeah, we can, for any of these, we can just draw a picture real quick. So here's A, here's B, here's, I need more overlap. Sorry, bad picture. Oops. Make sure that we can see all the overlaps. So we'll call that one A, that one B, that one C. So if we got you're in A or you're in B and C, that's going to be everything in A or in both B and C.
Oh, okay.
So here's B and C. And then A gives us all this too, right? A or B and C. That's the same as A or B and A or C.
Okay.
So A or B is these two sets, but you need it in A or B and A or C. That's going to give you all of A plus this. So it needs to be in A or it needs to be in both B and C. Is the same as it needs to be in A or B and A or C. Good? Feeling the intuition's clicking? Okay. This one should be pretty easy. A cross B union C, just A cross B union A cross C. Everything in A paired with everything in B or C is everything that's paired, everything in A paired with B, or it's everything in A paired with C.
yeah.
That one good? Yeah? Okay. This one, everything in A paired with everything that's in B and C is everything that's in A paired with B and in A paired with C.
That one's intuitive.
Okay, that one's more intuitive?
Yeah.
Okay. Everyone good on that one?
Yeah.
Alright. And then we have everything in A, all the left-hand elements in A and the right-hand elements are in B but not C, is left-hand elements in A and in B but not A and in C.
But right hand not in A and C.
Take all the A's paired with B's and then get rid of all the A's paired with C's.
Alright.
That's all the A's paired with things that are in B but not C.
Why do you have the minus sign instead of the not sign?
This is not logic, this
Um,
is sets. So I've been saying or, but that's union. It's just what is B union C? Remember, we use logic to build math, so I define everything in terms of logic. So when I want B union C, that's the same thing as a set of all x such that x is in B or x is in C. So I have to take this and define it in terms of logic and propositions, and then this now has meaning. So that's why when I say it's in B or C, that's why I read union that way sometimes to try and help the intuition. So here, we're talking about set subtraction.
Okay.
We're not talking about not. We're not talking about the logical operator not.
Okay.
Okay, so we good with this one? Is this what we just did?
Yeah.
Everything in A paired with things that are in B but not C, or things in A paired with B but not things in A paired with C.
Yes, you said the same thing right twice.
Okay. Now, these ones were just unintuitive, right? So we did proof of them. Let's see if we can get them to build our intuition. A minus everything in B or C is everything in A minus B and A minus C. So it has to be in A and not in B, and in A and not in C, to be in A and not in B or C.
Actually, that helped me.
Okay? If it's in A and it's not in B or C, then it's in A and not in B, and it's in A and not in C.
Okay.
Right, that kind of makes sense.
Okay, now let's do this one. Everything that's in A and not in B and C is everything that's in A and not in B, or it's in A and not in C. That's everything that's in A and not in both B and C.
Right.
If it's not in both B and C,
Can't be one.
then it's not in B or it's not in C.
Right.
Feel like good? Okay. So we're just going to have to use those things a lot, so want to try and make them appeal to your intuition. That way when we use them in a proof, helps connect. I don't know. I'm sure that over and over again we're going to have to come back and stare at one of them for a second and be like, oh yeah, that does make sense. Okay, now we're ready to move on to relations. For some of you, this is the nth time that we've covered relations. And as I tell you every time we cover it, they're in all of math and they're going to keep covering up no matter what field of math you're in, so make sure you understand them. And for those of you who don't understand relations, make sure you understand now, and let's go over them. We're only going to talk about relations from a set to a set. So, given sets x and y, a relation R from x to y is a subset of x cross y. So what's x cross y? That's all the ordered pairs where the left-hand element comes from x and the right-hand element comes from y. Right? Huh?
The relation is R.
A relation R is just a subset of this.
Maybe finish your whole proof and I might see it, or your statement.
Well, that's it for what a relation from x to y is. Then we just say x is related to y, and we denote it by x related to y, provided that the ordered pair xy is in R. So R is a subset of x cross y.
Okay.
So we can think about, if we're talking about, say that x is a set 1, 2, y is a set 3, 4, then x cross y would be 1 goes to 3, 1 goes to 4, 2 goes to 3, 2 goes to 4. Right? If x is a set 1, 2, and y is a set 3, 4, then x cross y is this. These are all the ordered pairs you can make where the left-hand element comes from x and the right-hand element comes from y. Any subset of this you pick is a relation from x to y.
Yeah.
Right?
So if you pick 1, 3, and 2, 3.
Yeah, so this, 1, 3, 2, 4, there we go. There's a relation. That is a subset of this.
Right.
Question, is the empty set a relation?
Yes.
Is the empty set a subset of this?
Yes.
Yes. Everything in there is in there. There's nothing in there. Right?
Right.
Something being in there implies it's in there. That's true, because nothing's in there. So the implication has a false antecedent, and the implication with the false antecedent is always true. We call it vacuously true. There's no cases to check. So this is a relation. This is a relation. A relation from x to y, a relation from x to y. Good? What about the whole set? Is this a relation from x to y?
Mm-hmm.
Yes, every set is a subset of itself. Is everything in this set?
Yeah.
Then it's a subset of it. questions on a relation from x to y? Should have kept that written up, because then what do we mean for x to be related to y? We mean xy is in R. If x is related to y, we say xy is in R. Let's come up with a relation real quick that you're already familiar with. Let's look at the less than relation on the real numbers.
Okay.
So the less than relation is a map from the real numbers to the real numbers. So the less than relation is equal to, we can't draw everything in here, but what's something in here? Well, we have 0, 5 in there, because 0 is less than 5. We have negative 2 pi in there, because negative 2 is less than pi. We have, what else?
3/4.
3/4.
4/4.
1. And there's infinite things in here. That's the less than relation. So when we say that 0 is less than 5, that's the same thing as saying that 0, 5 is in the less than relation. So a lot of the times we don't like writing it this way, we'd rather write it this way. So if x is related to y, that means xy is in R. Rather than always saying xy is in R, we like to write it this way when we're talking about a relation, as you've obviously done 100 times with the less than relation, the less than or equals than relation, the congruent relation, the equals relation, the subset relation that we've been using, that is a member of relation. Of course, we can't define it in terms of itself, so maybe we can't use it as a member of. Anyways, so that is a relation. A relation from x to y is just a subset of x cross y. And we say that x is related to y, provided that xy is in R. Feel like you got a understanding of all that?
Mm-hmm.
Now, a relation on x is just a relation from x to x. Or in other words, our relation is just a subset of x cross x. So we had a relation from x to y. Now you can just take a relation from the set to the same set. There's no problem with that, in other words. It's okay to do a relation from x to y. It's okay to do a relation from x to x. They're both fine. We just have a special way of talking about a relation from x to x. We just say that it's a relation on x instead of relation from x to x. Good with that? Okay. Now, another thing I tell you, if we're going to talk about relations, what's a special type of relation we're going to talk about? An equivalent relation. These also come up in every field of math. A relation R on X. So R is a subset of what?
X.
X cross X.
X cross X, yes.
A relation R on X, if R is a relation on X, is a subset of X cross X. It pairs elements of X with elements in X. It's a set of ordered pairs where its ordered pairs come from X. Both the left and right hand element. Okay, so a relation R on X is called an equivalence relation, provided that for any 3 elements you pick in X, 3 conditions hold. 1. X is related to X. This has to be true for everything in X. X always has to be related to itself. 2. If X is related to Y, then Y has to be related to X. 3. If X is related to Y and Y is related to Z, X has to be related to Z. We call X related to X the reflexive property. We call X related to Y implying Y is related to X the symmetric property. And we call X being related to Y and Y being related to Z implying X is related to Z transitivity. And it doesn't matter. Transitivity. So reflexive, symmetric, transitive. If a relation is reflexive, symmetric, and transitive, we call the relation an equivalence relation. So let's go through some examples of relations on sets, and you're going to tell me whether or not it is an equivalence relation. So let's look at equals on the set of real numbers. Let's go through it. Is it true that for any real number, it is equal to itself?
Yeah.
Okay, so it's reflexive, it's reflexive. If x equals y, is it true that y equals x?
Yeah.
Then it's symmetric. Is it true that if x equals y and y equals z, that x equals z?
Yeah.
Yeah. Okay, so it satisfies those 3 properties. then yes, this is an equivalence relation. Next one, let's look at congruent on the set of all geometric figures.
Okay.
You understand what I'm saying?
Yeah.
Just basic geometry. Is it true that every geometric figure is congruent to itself?
Yeah.
Yes. Is it true that x is congruent to y, y is congruent to x?
Yeah.
Yes. Is it true that if x is congruent to y and y is congruent to z, that x is congruent to z?
Yeah.
Yes. These are three of your axioms. If you use Hilbert's geometry, these are the three axioms that congruence satisfies. It's an equivalence relation. Okay, so yeah, this was an equivalence relation. Let's look at this has the same mother, I said same mother, and it has the same mother on the set of people. Is it true that I have the same mother as myself?
Yes.
That's true for anyone, right? So yeah, that's reflexive. Is it true that if I have the same mother as y, y has the same mother as me?
Yes.
Yes. Is it true that if x has the same mother as y and y has the same mother as z, that x has the same mother as z?
Yeah.
You mulling that one over?
Yeah. X is the same number mother of y, and y has the same, yes.
Yes. Okay. So yeah, congruence relation. Alright, let's look at less than or equals on R. Is it true that x is always less than or equal to x?
Yes.
Or equal to, yeah.
Yeah. Is it true that if x is less than or equal to y, y is less than or equal to x?
No.
No! 2 is less than or equal to 7. 7 is not less than or equal to 2. So it's not symmetric. And then let's check the last one anyways, even though we already know it's not an equivalence relation. It's worth getting comfortable with these properties in general. Is it true that if x is less than or equal to y, and y is less than or equal to z, that x is less than or equal to z?
Yes.
Yeah.
Yes. If x is less than or equal to y, and y is less than or equal to z, x is definitely less than or equal to z. Yeah, but it didn't have this one, so it is not an equivalence relation. Alright, let's look at common parent. Does x have a parent in common with x?
Yeah.
Yeah? Always?
Mhm.
Yes.
Okay. Means reflexive.
Not in today's generation.
How?
They changed. All of a sudden they find themselves as a sky.
Do they have a parent?
Huh?
Do they have a parent?
Now the cloud's their parent.
Doesn't matter, as long as it's still their parent.
But their real parent.
You either don't give them a parent, in which case it's vacuously true, or you give them a parent, in which case it's their parent. So, you have a hard time getting around that one. Okay, next one. If x has a common parent with y, does y have a common parent with x?
Yeah.
Yeah.
Yeah. If x has a common parent with y, and y has a common parent with z, does x have a common parent with z?
No.
No?
No.
Yes.
I'd say yes.
No. I have a common parent with James. James has a
Boy,
Uh,
girl, boy, girl. So boy and girl have child A. Girl and boy have child B. Boy and girl have child C. A has a common parent with B. B has a common parent with C. A does not have a common parent with C. So, no, not transitive.
Gotta remember, divorce is gossip around.
We're in a square. Okay. So, no, this one was not an equivalence relation. Alright, so there's some examples of equivalence relations to try and get you comfortable with it. More notation. When you see R, the set of all real numbers to the power of 2, that just means R cross R. And there's a general rule when you see R to the n, that just means R cross R cross R cross R n times.
I feel like we already went over that.
I don't know if we did that notation specifically, but I want to make sure that we understand it, because we also have special names for these. I call this R2. I don't call R to the power of 2. I don't call it R squared. I'm going to say R2. When I say R2, I'm talking about this. When I say R3, I'm talking about, I was going to say three-dimensional space, but, right? basically same thing. We can map all the points in R3 to three-dimensional space. And if I say R4, then you know what I mean. And R1 obviously is just R. Okay, so now let's do a somewhat more involved example of an equivalence relation. So on R2, so you can think about this as a real number plane. So we're talking about all the points on the plane, R2. With me so far?
Mm-hmm.
On R2, define the tilde relation. It's just, I'm coming up with a name for it.
Okay.
I could have used R, I could have used anything I want. It's very common that we use a tilde for a generic relation or an R for a generic relation. These are the two common things we do.
Oh.
Okay.
I thought you said Matilda.
That's what I thought you said.
Matilda.
The tilde relation. Okay, so we're just coming up with a relation off the top of our heads. I'm going to call it the tilde relation. It takes, so this point in R2 is related to this point in R2, provided that the sum of these two is equal to the sum of these two.
That means
Okay.
Notice that this is a pair of real numbers. We know how to add on the real numbers. This is a pair of real numbers. We know how to add on the real numbers. So we know how to do this.
Wait, aren't we crossing these up? R2 means we're crossing first one and second one.
So what does my tilde function look like? Tilde is a function from, oh, we haven't seen that notation yet. What is tilde a subset of? Tilde is a subset of R cross R cross R cross R. Right? It's taking elements in this and pairing them with elements in this. It's taking points and pairing them with points.
Oh, tilde is just a subset of that, so yes.
Yes,
And
tilde is a subset of this.
That's its special property right there.
Yeah, how do I know if a point in here is related to a point in here? This. Are the sum of their coordinates equal? If the sum of their coordinates are equal, I may call them related.
Okay, yeah.
Now, this, I'm going to take a pause for a second to make a note that I made earlier, but here's a better place to demonstrate it. I told you that as we go through the book, the author is going to assume, notice that we're using all sorts of math here that we haven't developed in this class. We're using plus, we're using equals, but we're doing it inside of an example. So I told you that the author is going to assume all sorts of other maths, all sorts of other understanding that you don't have in the examples to help give you intuition for things. But then when we go back to our definitions and our theorems, we won't be using stuff like this. Make sense what I'm saying?
Perfect.
Yeah.
Yeah. Okay, so we're going to be talking about this. We're going to be talking about graphs of lines. That's not because that's necessarily in the field of topology. That's just examples in fields that you most likely already have come across before to help give you a more involved example of an equivalence relation. Okay. So on R squared, we define the tilde relation by 2 points are related by tilde, provided that the sum of their coordinates are equal. So then we're going to show real quick that tilde is an equivalence relation. With me so far?
Yeah.
Alright, first off, is it reflexive? Is it true that for some point P1, P2, that point is always related by tilde to P1, P2?
Mm-hmm.
Yes. P1, P2 is always related to P1, P2 since P1 plus P2 is equal to P1 plus P2.
Oh, yes.
Notice that this is true if this is true. This is always true, so this is always true.
Why wouldn't you put Q1, Q2 right there?
I'm just naming them. Could have called it whatever I want. I could have done it like this. X1, comma, Y1 is always related to X1, comma, Y1.
No, I'm saying like tilde, so X1, Y1.
I need to show,
P1.
I need to show X is related to X. If I'm showing it's reflexive, I need to put the same thing on both sides and make sure it's always true.
Okay.
In this case, I just picked P1, P2.
Okay, I was thinking like the whole statement itself, not just one side, but that makes sense.
Okay, so yes, this thing is reflexive. Alright, now let's show it's symmetric. So I need to show that if P1, P2 is related to Q1, Q2, I need to use this to show that Q1, Q2 is related to P1, P2. Right? That's what we're trying to show. Okay, so if I know that P1, P2 is related to Q1, Q2, what do I know?
P1 plus P2 is equal to Q1 plus Q2.
Yeah, P1 plus P2 is equal to Q1 plus Q2. Okay, if I know that, then what do I know?
Then you know P1 plus Q2 is equal to Q1 plus P2. That's
You're right.
not true.
Then we know that Q1 plus Q2 is equal to P1 plus P2.
Oh, you flip it that way.
Yeah, just flip it around. And what does that give us? That gives us that Q1 comma Q2 is related to P1 comma P2. Right?
Oh, okay.
That's all we were trying to get. So now,
You are the one. Don't do that.
alright. Now, let's move on to the next one. Now we're trying to show what's transitive. We're trying to show that if P1, P2 is related to Q1, Q2, and Q1, Q2 is related to R1, R2, that P1, P2 is related to R1, R2. Right? That's what we're trying to show. So if we know this and this, what do we know?
P1 plus P2 is equal to Q1 plus
Yeah, we know P1 plus P2 is equal to Q1 plus Q2. And we know that Q1 plus Q2 is equal to R1 plus R2.
Right.
Yep.
Right?
Mhm.
So that gives us that P1 plus P2 is equal to R1 plus R2, which gives us that P1 comma P2 is related to R1 comma R2.
So we just learned that they have an equivalence relation.
Yeah, we just showed that this relation is in fact an equivalence relation. So we just made up a relation, however we wanted, and we showed that it's an equivalence relation. Good? Any questions so far? Okay, now what is this equivalence relation that we created? Let's look at it for a second. So pick some point A1, A2 in R2. Pick any point we want out of there. And let's look at all the xy. Let xy be any point related to A1, A2. So if xy is related to A1, A2, what does that mean? That means x plus y is equal to A1 plus A2, which gives us that y is equal to negative 1 times x plus A1 plus A2. And notice that this is the equation of a line, right? Y
Yeah.
equals
yeah.
mx plus b is one way that you're used to seeing this.
You're saying algebraically if we flip things to the right side.
What do you mean if we put things to the right side? Y is equal to mx plus
I'm saying,
a
how'd you
constant.
get that? You got that? Yes.
I moved the x to the other side.
Algebraically, yes.
Subtract x from both sides,
Thank you. So much.
right?
Yeah.
Thus, all the points xy related to a1, a2 are the points on the line y equals negative 1x plus a1 plus a2. What are all those points? Those are all the points that go through a1, a2 with the slope negative 1.
Right.
So pick a point, draw the line with the slope negative 1 through that point, and those are all the points related to a1, a2. Pick any point on here, it would be related to a1, a2. Pick a point over here, it would not.
So the relation we just built, you're saying this, what do we call the generic
A
relation?
point is on this line if and only if it is related to a1, a2 under our relation.
Right.
So if I know a point's related to a1, a2 under our relation, I know it's somewhere on this line. If I pick any point on this line, I know it's related to a1 and a2 under our relation.
Yeah, I'm not getting it, actually. Because shouldn't that mean the addition of those 2 points equals the addition of a1 plus a2?
Yeah, pick any point you want on here.
Can we use numbers real quick?
We sure can. So let's, we'll come over here. Well, we need to reference this again. We won't need to reference this again. So get rid of this. And let's do one. Give me a point.
1, 2.
1, 2.
That's
Okay.
your a1, a2.
A1, A2.
Yeah.
So y plus A2, 3.
Mhm.
What is some pair XY that satisfies this relation?
2, 2, 4? No, 2, 3. Is it 2, 3?
So you're saying pick 3 for X. Just pick an X.
2.
2. So if we pick 2 for X, negative 2 plus 3 is
1.
1. So negative 2, oh wait, we picked 2. So 2, 1 is on the line. Notice that some of those and some of those, same thing.
Oh, we're just plugging in any X, you're saying.
Pick any X you want.
7.
Let's go look at negative 97.
Okay.
Alright, when we plug that in, what do we get? 100. Add those up, you get the same thing you get when you add those up.
They do 100.
So negative 97, 100, we're up here somewhere, is on the line.
Right, that's cool.
Good?
Yeah.
Okay. So that's what we did. And notice, if we picked another point, and we talked about all the points related to it, it would just give us another line with the same slope. Right? So for any point you want, pick a point. There's going to be a set, or there's going to be a set of points, or a line of points, all related to that point with the tilde relation.
You're with this tilde relation. You're
Yeah.
just saying this is equal property.
So I could take all my points on my xy plane, and now I could assign them to a line. I take all the points here and I assign them to this line. I take all the points here and I assign them to this line. All the points here I assign them to this line. All the points here I assign them to this line. And I can split up all my points and divide them up into just sets of lines, right?
Right.
And that would be an example of what we call a partition. So a partition is a set of sets whose union gives you back the whole thing. So I'm saying that if I look at all the lines that we can get, notice that there's infinitely many of them.
Yeah.
And if I were to take the set of all those lines,
Yeah.
L1, comma, L2, comma, L3, and all of them, notice that every point is going to be on one of these lines. For any point you want, it's going to be on one of those lines. And it's going to be on one and only one of those lines. It's not going to be on two of them because they're all parallel lines so they don't intersect.
Right.
So I can take every point and assign it to one and only one of these lines if we think about these lines as sets of points.
So we're saying it's equivalent to the plane.
Yeah, so I'm saying if you were to union up all these sets, you would just get back out R2, right?
I now understand why that first theorem we proved.
Yeah, you could use the union lemma to prove this if you wanted. Every point in R2 is in one and only one of these subsets. All of these things are subsets of R2, therefore when you union them up, you get R2. Yes, using our union lemma that we just erased and said that we wouldn't need to reference again for this class. But another way that we can say it is this is a partition on R2. So a partition on a set is when you take every point in the set and assign it to one and only one subset.
Okay.
So if I pick a point in here, namely 1, 2, it's going to be on one and only one of these lines. It's not going to be on two of them. Or in other words, if I look at all the points on this line and this line, what points are they? What are all the
Each
points
other.
on this and this?
They're not each other.
The empty set. None.
Yeah.
There aren't any points on this line and this line. So these are mutually disjoint. This is a mutually disjoint set. Any two lines here are disjoint, so the whole set is mutually disjoint. And so a partition on a set is a collection of subsets whose union give you back the initial set and that are mutually disjoint. So let's give you our next definition here. A partition on a set X is a collection of mutually disjoint subsets of X whose union is X. Right? So the lines that we just made here, we took the plane and we divided it up into lines. Those would be a partition on the set. Now, notice another way to think about all the points on the line is it was all the points related to A1, A2. Right? So we would call all those points the equivalence class of A1, A2. And we symbolize it like this. We do square brackets and then an element. So our element was A1, comma, A2. And we put those in square brackets like that to symbolize the equivalence class. The equivalence class of A1, A2 is a set of all points related to A1, A2. In this case, it's just this line.
So it would be
The
one
equivalence
line
class
and
on 1, 2, would be the set of all the points on this line. You with me?
Yeah.
So notice that the equivalence class 1, 2 is the same thing as this line, which is the same thing as one of the members in our partition.
How are we going to think about this without using lines?
Another way that we can do it, pick an equivalence relation for this class. Has the same last name. Has the same last name as equivalence relation. You have the same last name as yourself. If you have the same last name as me, I have the same last name as you. If you have the same last name as me and I have the same last name as Jack, you have the same last name as Jack. Okay, so has the same last name as equivalence relation. Notice now if we divide it up into groups, so that you pair with everyone who has the same last name as you.
Partition. That's partitioning, right?
Then we just created a partition.
Right.
If you union up all the groups of people, you get back everyone in the class.
Right.
Similarly, and also, everyone shows up in one and only one of those groups.
Right.
Right? So we can say the equivalence class on Jacob is all the people who have the same last name as Jacob, including Jacob.
Right.
Or we can say that that's everyone who's in the same part as Jacob. When you have a partition, we call the things inside the partition the sets in their parts. You with me?
Right.
So when you partition a set, you split it up into subsets where every element of the set shows up in one and only one of those subsets. Similarly, if you have an equivalence relation on a set, then the equivalence classes create a partition of the set.
What do you mean equivalence relation on a set?
Tilde on R2 is an equivalence relation on R2.
Okay.
And so it divides, if we look at all the equivalence classes, all the lines, those end up creating a partition of the set.
Yes.
So you can use partitions to create equivalence relations, and you can use equivalence relations to create partitions. Right?
Yeah.
Notice if I decided to, say I started out with this partition, these lines, I can come up with an equivalence relation called is on the same line as.
Right.
And then that would also be splitting these up the exact same way. Right? Because this point would be on the same line as this point. That would give me the same equivalence relation that this is. This is just another way of saying it. So I can go from a partition to an equivalence relation, and I can go from an equivalence relation to a partition. The equivalence classes are just give us a partition on our set. So that's what we're trying to stress over here. So let's cover these three things. A partition on a set X is a collection of mutually disjoint subsets of X whose union is X. That was pretty straightforward. Let R be an equivalence relation on X, and let little x be an element of big X. Then the equivalence class of little x is a set of everything that X is related to. And it's called an equivalence class. So,
that's not saying the same thing.
yeah, it is. Come over here. A1, A2 is something in there. And here's our little x.
Okay.
Now we're going to look at the set of everything related to little x.
Right.
That's this line.
Right.
So, our equivalence class is a set of everything that x is related to. It's a set of all the points, in this case, in this example over here, that x is related to. If the equivalence class was Jacob and the relation was has the same last name, this would be the set of all Timsons. Right?
Okay,
So,
real quick, because you've said it a few times, but let R be an equivalence relationship on X.
yeah, on the
R
set.
cross.
So R is a subset of X cross X. R takes elements in X and pairs them with elements in X.
Right. Right.
Getting it?
It's a subset of it.
R is a subset of X cross X.
Yes. R is your relation. R is your little
R is your
squiggly
relation.
line or whatever.
Yes. When we do all these lines, well, yeah, when we look at all these, well, I don't want to say it that way. Never mind. I think you have it. So let's move on. Let's see, which one were you stuck on? You were stuck on this one. Okay, next. The note that I was stressing before. The collection of equivalence classes are a partition. When you have an equivalence relation, and you split everything in the set up into their equivalence classes, you end up with a partition. When I have my relation tilde, and I split up everything into separate equivalence classes using tilde. In other words, I draw all these lines. I just partitioned R2. So equivalence classes give us partitions. Okay. And then I said what we were already talking about over here, so we can ignore that next part. Good? All right. So now let's move on to functions. So we talked about relations. Next, we're going to talk about functions. What's a function? A function is just a special type of relation. Let's just go over the definition. So let x and y be sets. Then a function f from x to y, just like we had a relation from x to y, a function f from x to y is a relation from x to y, such that for all x in x, there exists one and only one y in y, such that x, f, y. F's the name of our relation, right?
Is that a little x and big X? Or is
Yeah.
that X?
For all little x in big X, there exists one and only one little y in big Y, such that x is related to y.
Perfect.
And we don't like this when we're talking about functions, f related to y this way, so we write f of x equals y instead. But this just means this. Good? So, you're good with this dense notation? I thought I'd have to go over that a lot more, but
No.
you got it, you got it. Okay. So we write f of x equals y, and we call y the image of x under the function f. If you remember clear back to our axioms on set theory, one of our axioms, one of the definitions that we need to create for our axiom was this exact thing. What do we mean by the image of x under the image of x under f? What do we mean by that? And we have to come up with the definition for it, so we're being introduced to the exact same thought here again, because what we were doing over there, our axiom said that the image of a function is still a set. That's what the axiom was giving us,
Yeah.
right? So we have seen this before already with set theory, but there it is again. So we call y the image of x under f. The set big X is called the domain of f, and the set y is called the codomain of f. And we typically write f as a function from x to y. So if you ever see f colon x arrow y, this is shorthand for f is a function from x to y. So you instantly know when you see this that f is a subset of x cross y, right?
Can you write an example?
Sure. Here's x, 1, 2. We're off the camera if we did that. I don't think we'll need this anymore. Of course, right after I erase it, we'll start referencing it. So, let's pick some set x equal to 1, 2, 3, 4. Y equal to 1, 1, 2, 2, 3, 3, 4, 4. We'll mix it up a little bit to make it not so clean. So here's a set x, here's a set y. Now we're going to create a function from x to y. What is a function from x to y?
X.
It's a relation, so we're going to call it f. It's a relation that maps everything in x to one and only one thing in y. Right? So I can map 1 to one and only one thing in y. In this case, I'll map it to 4, 4. Now, I need to take 2 and map it to one and only one thing in y. In this case, I pick 4, 4. I need to take 3 and map it to one and only one thing in y. In this case, I pick 4, 4. And then, I need to take 4 and map it to one and only one thing in y. In this case, I pick 1, 1. There is a function from x to y.
Okay.
So f is a function from x to y. Notice that it is a subset of this cross this.
Right. For sure.
Okay.
For sure. Notice also that it mapped everything in x to something.
Right.
So it uses all of this, it doesn't necessarily use all of this. It could use all of this, but it might not use all of this. Now, let me try one more thing. What if we also did 1 goes to 3, 3? Is this a function?
That's probably one only.
This is a subset of x cross y, and it maps everything in x to something in y. Why doesn't this work as a function?
One and only.
Because one of its elements are mapped to two
Y.
things.
Right, we have one map to that, one map to that. We said for all x in big X, there must exist one and only one thing in y such that x is related to y. Or in our case it was a function, so x is related to y. And in our case, here we have 1 is related to 4, 4. And we also have 1 is related to 3, 3. That doesn't work.
It's not a function.
Another way that you could think about whether or not it is a function, you could say, what is f of 1 equal to?
4, 4, or 3, 3.
You can't answer the question. So if you can't answer this question, if there's ever a case where you can't answer this question, then this notation that you're used to for a function isn't defined. So chances are you're not working with a function. But now notice if we get rid of this element, now if I were to ask you, what's f of 1 equal to?
3.
Then we know what it is. It's the point 4, 4. And what's f of 4 equal to? The point 1, 1. Right. Alright, so there's an example of a function on some set. And one that wasn't a function, even though it was still a relation. Notice when I put 1 goes to 3, 3 in here, that's still a relation.
Right.
It's still a subset of x cross y.
Right.
It's just not a function because it doesn't satisfy this condition. So it has to be a relation that satisfies this condition to be a function. Okay, any questions on that? And you're good with this notation? F from x to y? Okay, let's adjust our camera. Good enough. Okay. So now, couple more definitions, and then we'll do more examples to our heart's content to get comfortable with it. Okay, given that f is a function from x to y, and that a is a subset of x, then we define the image of a under f by f of a is equal to the set of all y's that a maps to. So let me say it intuitively, and then let's go over the definition exactly. What is f of a? It's everything that the elements of a map to. Right?
Mm-hmm.
Right.
So if a is a set 1, 2, then f of a is all the elements that 1, 2 maps to.
And A is just a subset of X.
A is a subset of x. Yeah. So now let's go over this definition exactly. I think you'll get it. Given that f is a function from a to y, and that a is a subset of x, then we define the image of a under f by f of a is equal to the set of all y and big Y such that there exists an x in a with f of x related, or f of x equal to y. Or in other words, x is related to y, right? F of x equals y, f of x is related to y. We're going to start wanting to say it this way rather than x related to y.
Just basically saying subsets of your domains.
Well, notice that over here, even though it's off the camera, we talked about y is the image of x. What does it mean for y to be the image of x? F of x equals y. Okay, now what's the image of a set?
Right.
It's everything that would be mapped to by that set. So we're extending the notion of image, so now it's not just talking about one element, it's talking about a set now. And so now we can talk about the image of the whole function. I don't know why the author doesn't say that, but now the image of the whole function, or what you've typically heard called the range, the image of a function is just f of the whole domain, x. That's the image. And then you've heard about, well, I'm sure we'll eventually get to 1, 2, and on 2, and bijection, but just keep going here. Okay, so you think you're comfortable with this definition? The image of a subset of the domain? Okay, so let's move on to what does it mean for a function to be a constant? A function f from x to y is called constant, provided that for all x and x, f of x is equal to the same thing. What's the function that you're used to?
X equals
F of x equals 1. What did you mean by this when you typically saw it in your math classes? You meant f is a function from the real numbers to the real numbers by f of x equal 1. That's what you meant by f of x is equal to 1. You meant every real number is just paired with 1. Right?
Mm-hmm.
Okay. And then the identity function. So, we define the identity function on some set x to be a function from x to x that maps every element to itself.
Is that little x or big X?
That's big X down there, the set. The identity on some set is a map from that set to that set where you just map every element to itself.
Key.
Does that make sense? Let's look at the identity on R. What does that equal to? Tell me something in there.
1 to 1.
1, 1's in there. We also have pi, pi in there. We also have
2, 2.
2, 2 in there,
So crazy.
etc. We take everything in R and pair it to itself. That's what this is shorthand for. The identity in R on
So
R.
that's big X, that's little x to your right.
Yeah, this is still a big X. Sorry.
But your other one's little x.
But that's little x, that's little x.
Yes.
Those are elements in X. Good. I should have specified that.
Okay.
Yeah. Okay. So, identity function just maps everything to itself. Does exactly what you expect it to do. Alright, so let's do some quick examples, make sure that we've got a handle on all this. So I defined 3 sets here. X, 1, 2, 3, Y, 4, 5, 6. A is just 1, 2. Notice A is a subset of X.
Mm-hmm.
Right? Okay, so first off, let's create some function. 1 goes to 6, 2 goes to 4, 3 goes to 5. Okay. What's f of A then?
1, 6.
1, 6,
2, 4.
2, 4. 1, 6, 2, 4.
Sorry, 6, 4.
6,
Yeah,
4.
that's just 6.
Sorry, yeah.
Just 6, 4, right?
Yeah.
The image of A is everything that gets mapped to from A. So 1 goes to 6, so 6 is in there. 2 goes to 4, so 4 is in there. And that's all that's in there. Okay.
Okay.
What is the identity on X?
1, 2, 3.
1, 1, 2, 3?
Yeah.
Like that? That's the identity function on X?
No?
No.
It's
No, that's not even a
Yeah.
function, let alone a function from X to X. So what's in there? This is the identity function on X. What's X? 1, 2, 3. What does the identity function do?
Maps it to itself.
Maps it to itself.
Maps it to itself. So what's the
one,
first thing in here? 1, 1. Okay.
2,
2, 2. 3, 3. That's the identity function on X.
Okay.
What's the identity function on Y?
4, 4, 5, 5, 6, 6.
Oops. 4, 5, 5, 6, 6. Wonderful. Okay, so there's examples of the image of a set, the identity function, and then just a function from a set to a set. Good?
Well, can we do some more examples?
So more examples? Sure. Give me the sets you want to do. We'll just do them down under here. Sit down. Right? What do you want X to be?
I don't know. Something creative.
What do you want Y to be?
EFG.
Alright, so let's make a function from X to Y. So we're making F from, F, if we want to be a function from X to Y. And how are we, it's just going to be from X to Y. I'm just going to write F equals though. So F is equal to, we need to take I and map it to something. What should we map it to?
F.
IG.
F. We need to take D and map it to something. What do we want to map it to?
E.
E. We need to take K and map it to something. What do we want to map it to?
E.
E. Okay. Notice this is a function from X to Y. It maps everything in X to something in Y, and everything in X is mapped to only one thing in Y. I don't have I mapped to F and I mapped to something else. In other words, if I were to say, what is F of, and I put any letter in X here, you know what it is. If I put I there, then you know that that's equal to what?
F.
F. Wonderful. Okay. So there's our function. Now let's give me any subset of X you want.
Any what?
Give me a subset of X.
ID.
ID. So what is F of ID equal?
F. E.
FE.
FE. Notice that the image of a set always gives us a set,
Okay.
right? The image of some set is just a set. That was what our axiom was. If you go clear back to set theory, the image of any set is just a set. The image of a set, that already implies you have a function. Okay. I guess we can look at the identity on, we'll just pick one of them,
What?
X.
X.
What's the identity on X equal to?
I.
I.
DD, and KK.
Ku Klux Klan.
No, just KK.
Ku Klux.
Because then you super agree.
Ku Klux.
Alright. Want to see another example?
No.
Think you got it?
Yeah.
Okay. So now, look on that camera real quick and tell me when I'm going off.
Okay. You're off.
Am I off?
No. You're bare wheel.
Can you see that line?
Doesn't matter. I can see that. Just don't want to go too far. Okay. Let's get a Greek math.
So are we done with chapter 0?
No. Not by a mile.
Your line.
Really?
Oh my gosh.
No, we're almost done. Kind of. I'm not sure where we are. Let's see, functions, we went over that. Given that F, yeah, we've only, if you're following in the book, we just have done definition 0.19.
1.9?
Yeah. So now we need to do definition 0.20.
What the heck? Because I was looking at those and I was like,
Alright. So next.
we actually still have about.
This is definition 0.20. So, given that f is a function from x to y, so given that, and given a point y in capital Y, comma, we define f inverse of y throw some vernacular in there. Let's see, 20, comma, to be the set of all little x and big X such that f of x is equal to y. Finish the definition with an example. And then similarly, let's see, where were we? Given that W is a subset of Y, we define F inverse of W, which is also called the preimage of W, to be the set of all little x in big X such that f of x is in W. Okay, so this is like doing the inverse of what we were doing before. So we were taking things in X, mapping them to things in Y. Now we're looking at it backwards. So let's look at some function. We could just use one that we already have written here. Well, let's we can use this one. Let's look at this last example that we just did with all these letters. So when I'm looking at these letters, what is the pre-image? F inverse of, looking at this example over here, let's see, why was this? What is the pre-image of E equal to?
D and A.
E. Yeah, everything that mapped to E. D mapped to E, K mapped to E, so it's D comma K.
Okay.
What is the pre-image of, what's the next one?
F.
F.
I.
I.
Poor G. It's gonna be long.
Oftentimes when we talk about the pre-image of an element and it just has one element, sometimes we neglect to talk about it as a member of a set. So, just warning that I might accidentally do that. I'll try not to do it without explicitly saying so. Anyways, and then let's look at the pre-image of G.
Empty set.
Empty set. Wonderful. Now let's pick some subset W equal to EG. Then what is the pre-image of W equal to?
DK.
D comma K. Follow all that?
Oh. Yeah.
Anything weird? Anything you don't like?
Can we do another one?
Sure. Let me think. Well, black ball is stress on me. Give me a set X,
Square, circle, triangle.
square, circle, triangle. Give me a set Y,
Line, dot,
Star.
star.
line, dot, star. Give me a function. What do we want to pair a triangle with?
Line.
Triangle goes to line, well, obviously. Then, square goes to what?
Dot.
I don't know, seems more to star to me. And then circle goes to
Star.
line again.
Nice.
Don't you see the pattern? There's no pattern. Alright, so now, what is the pre-image of line?
Triangle and circle.
Yeah.
That is equal to triangle, comma, circle. What is the pre-image of all of X equal?
Triangle, circle, star.
circle.
Triangle, circle. The stars.
Nothing in F maps to star. Oh.
Oh, there
Whoa,
was
we got way off.
line and
Pre-image of Y. Sorry, not X. Can't talk about the pre-image of X. Who let me write that? Okay. Pre-image of Y is what? Triangle and circle. Okay. Now let's try. And let's go back even further to reference some of our older stuff. What is f of square equal to?
why is square not part of the pre-image of Y?
That's what I was wondering. I just sat there and kept looking.
Y is square.
Stars map to square.
Let's see.
So you just wrote FX.
The pre-image of Y is, oh, thank you. I forgot why I was making a point, because I made the mistake of writing X. The point is, the pre-image is always all of X, when we do the pre-image of everything, right?
Okay.
That was the point I was going to make, and I got confused. The pre-image, if we do the pre-image of Y, it always has to be all of X, because all of X was mapped to something. That was the point I was getting. Okay, and what is f of square?
Star.
Star. And what is f of line? Doesn't make sense. Not the empty set in this case. So it's only when we're going from Y to X that we're always in terms of sets. Notice going from X to Y just means that they're related, right? Over here. F of X is equal to Y means X is related to Y. So f of something is always just going to be something. And when I do f of something that's not in the domain, that's undefined. That's like dividing by 0. No, it doesn't make sense.
Right.
Okay. Feeling good?
Yeah.
Okay. So let's get rid of all that and come back and just continue with our stuff. Okay. Theorem 0.21. Theorem 0.21. If f is a function from x to y, with a and b
If we all have a book.
as subsets of x. Yeah, this book helps because it puts a lot of graphics in there. So if f is a function from x to y and a and b are subsets of x, I don't know why I said with, and a and b are subsets of x, comma, then we have the following. Then 1 f of a union b is equal to f of a union f of b
I watched it with Dad.
2.
Jesus.
Yeah.
Same with the intersect, same with the difference with
I actually realized what they did to you.
f of a intersect b
You caught up.
is equal to f of a
Revenge.
intersect
In
f
real life.
of b,
Even though what they were trying to teach you wasn't that.
and then
And then it just stops you in your tracks.
this one was
I
reversed.
didn't like that, but I still thought it was cool.
No, that was the best.
The ending was
3
No, the whole boy was literally.
f of a
Boy, it was still
minus
defined.
f
You would
of
have thought
b
anyway.
No,
is
the whole
equal.
And then
Why did you write it
zero.
backwards? You must do subset. Is a subset. And was the other one a subset? Yes.
Trying to get you to sit in
Alright.
that Coliseum and watch those.
Is a subset
And cheer.
of f of a
And then
minus
you stop in your tracks
b.
and realize what really matters. That's why.
See,
Okay.
that's genius.
So let's go over each of these, make sure they make sense. do a proof of it if we need to. So if we take everything, take F and map everything in A or B, then that would be the same thing as everything that A maps to or everything that B maps to.
Wouldn't that just be all of X? Oh no, A
No.
and B are subsets.
A and B are just subsets.
They're not necessarily partitions.
So let's come up with an example over to the side. That line a little bit bigger so that I don't go past it. Let's come up with an example really quick. Let's do f of x is equal to, what do we want? We'll just do something like x squared, right? And then we'll take two subsets. So let's do A is equal to all the numbers from 0 to 1, including 1, and we'll do B is all the numbers from 2 to 3. You with me?
Yeah.
So what's f of A equal to?
1.
0 to 1.
All the numbers 0 to 1, right?
Yeah.
And what's f of B equal to?
All numbers 4 to 9.
All the numbers from 4 to 9. Oops, including 9. So what are we saying? We're saying, if we look at f of, I didn't make so that the union was nice. Maybe you can just see it and I don't need to write it. So now f of this set unioned with this set is just going to be this set unioned with this set. That's what this is saying.
Yes.
You good with that?
Mm-hmm.
Okay, let's look at the next one. Let's change our A's and B's around so that we can get an intersection. So A will make go from 0 to 2. B will make go from 1 to 3. That way they have some overlap. A intersect B is then going to be what?
1 to 2.
1 to 2. F of A is going to be
0 to 4.
0 to 4. F of B is going to be
1 to 9.
1 to 9. And then F of A intersect B is going to be
1 to 4.
1 to 4. So what are we saying over here? We're saying F of A intersect B, 1 to 4, is going to be a subset of F of A intersected with F of B.
How is A intersect B 1 2?
In this case, F of A intersect F of B is still equal. So when is it a subset and not equal?
How is A intersect B 1 2?
A is all the numbers from 0 to 2. B is all the numbers from 1 to 3.
All right.
So what are all the numbers between 0 and 2 and between 1 and 3? That's all the numbers between 1 and 2. Right?
Mm-hmm.
And then, here we got the intersection of A, B. We got it equal, we didn't get a subset. When is it going to be a subset? When can I find something that's in both of these that was not in this?
You do, don't you? Because
Oh.
that's 1 and 2 and that's 1 4.
No. What's the intersection of these two?
It's just 1 and 4.
Which is this. So the F of A intersect F of B is just equal to F of the intersection. So in that case it was equal. But now I've got the case where we don't get it equal. So let me think in my head for a second. Let's say A is equal to the set 1, B is equal set 2, and I have a function that maps 1 to 1, and it maps 2 to 1. So, what's A intersect B?
Just 1, 2.
A intersect B
Sorry,
is the
empty
empty
set.
set.
Right.
There's nothing in here. What is f of A?
2,
1,
1. What's f of B?
1,
1. What's the intersection of 1 and 1?
1.
1. So we had something here, but it wasn't here. So here's an example where they were equal. Here's an example where it was a proper subset. Good?
Okay.
And then, let's come up with one for the last one. F of A minus f of B is going to be a subset of f of A minus B. So let's see it in this example and see if it comes out equal. So f of A we have here, f of B we have here. A minus B. What's A minus B?
0, 4.
A minus B is going to be 0 to 1, not including 1. Take the set A and remove everything in B. And now, f of A minus B is equal to
0 to 1, but not including
0 to 1, not including 1. Same thing, right?
Oh, because we're squaring it.
We're squaring. Take everything in here and square it, and you get everything in here. Good? So, f of A, so in this case it is equal. F of A minus B is the exact same thing as f of A minus f of B. Right?
Yeah.
So there's an example where it's equal. Now see if we can come up with an example where it's a subset.
Just up your end.
So let's say A is equal to the set, let's see, 1. Oh, same thing. A is equal to the set 1, B is equal to the set 2. And then f is a function. F maps 1 to 1 and 2 to 1.
Okay.
So, what's f of A?
1.
1 minus, well, the second containing 1, minus what's f of B?
1.
The second containing 1. So that gives us just the empty set over here. What's A minus B?
1.
1.
The set containing 1, and then f of the set containing 1 is just the set containing 1.
Wait, why would it be -2?
What?
1 minus 2.
Set.
I know. I know.
Everything in A, which is the set containing 1, minus everything in B.
So you do nothing to it, I see.
Yeah, we didn't remove anything from A. So there's an example where it's a subset. So we get subsets in these two cases where we have two different elements being mapped to the same thing, and we get equals when we don't. Is what it looks like. Okay? Any of those you want to try and do a full proof for, or you want to keep going forward?
I like. Seems pretty intuitive.
You like? You want to just keep going forward?
Yeah.
Okay. So, now we're moving on to theorem 22, or 0.20, 0.22. This one has to do with inverses.
Oh, fun.
I know.
You should have kept on. Oh, you didn't.
Theorem 0.22.
You can just inverse.
If f is a function from x to y, and A and B are subsets, V and W, so we don't get confused with up there. And V and W are subsets of Y. Then we have the following three. One, we have F inverse of V union W is, these are all equal, is equal to F inverse, oh, now they're all equal, of V union F inverse of W. 2, F inverse of V intersect W is equal to F inverse of V intersect F inverse of W. And 3, F inverse of V minus W is equal to F inverse of V minus F inverse of W. Now, why did I say duh, they're all equal? Notice that the only time we had subsets in up here is when we had multiple x's mapping to the same y.
Right.
The only times we would be able to get subsets down here for the same thing is if we had multiple y's coming from the same x, which isn't possible with a function. So the bad cases up here become impossible when we talk about an inverse function.
Oh, you're saying,
Other than that, it's the exact same.
you're saying that's why it's not less than or equal. That's why
Yeah.
they're all equal.
Yeah, that's why it's always equal instead of just a subset. Does that make sense?
Yeah.
Okay. So you want to just keep going, or do you want to look at those?
You mean give us examples like you have it?
We can, yeah, we can look at examples if you want.
I like that.
Using that. Okay, let's look at some. So, this time, do you want a different function, or do you want to stick with that?
Stick with that.
Yeah, I like that one.
Okay, so we'll stick with that, and we'll call these things V and W. So, we're looking at the pre-image. Well, let's look at F inverse of V and F inverse of W. What's F inverse of V?
0 to the square root of 2.
0 to the square root of 2 union, or
No.
we don't need union yet, let's just take the whole thing. Negative square root of 2 all the way to square root of 2, right? This is the pre-image of this. Take anything in here and it maps to something in there.
All right. Yes.
What's negative square root of 2 squared?
2.
2. What's 0 squared? 0. What's square root of 2 squared? 2. This is the pre-image of this. This is a set of everything in the domain. Notice F here, obviously, but we didn't write it. F is a function from R to R, right?
Okay.
So it maps everything in R to something in R. So, what's everything in R such that their square is in here? It's this. Alright, what's the pre-image of W?
Negative square root of 3.
And square root of 3.
Negative square root of 3 to square root of 3, right?
Mm-hmm.
1 is just going to be in there.
No!
No, because
We don't have 0 in there. I can't take 0 and square to get something in there.
yeah.
It's the union of these two sets, right?
Oh.
Everything in here or in here, when you square it, gives you something in here.
Yeah.
Okay, so maybe this was a good function for pre-image, just for the sake of doing some pre-image stuff. Okay, now let's look at what we were actually talking about. So over here, F inverse of V union W. What's F inverse of V union W?
from the negative square root of 3 to the square root of 3.
Wonderful. Negative square root of 3 to square root of 3. Right?
Because
Yes.
Take V, union it with W, what do you get? You get everything from 0 to 3.
yeah.
Okay, what's everything such that when you square it, you get something between 0 and 3? Everything from negative square root of 3 to positive square root of 3.
I keep confusing union with intersection, is that what I said?
Now notice, what's the union of this with this?
The same thing, square root of 3.
It's just this, right?
Yeah.
If we draw a number line of this real quick, we're going to have negative square root of 3, square root of 3. We're going to have negative square root of 2, square root of 2. Then we're going to have negative 1, 1, and then 0 in the middle. Something like that, right?
Yeah.
So if we have this set goes from here to here, union with everything from here to here, and if we union that with everything from here to here, we're just left with everything from here to here, which is what this is.
Makes sense.
So, F of V union W is exactly, F inverse of V union W is exactly F inverse of V unioned with F inverse of W. See it?
Yes, now.
Okay. Now, I don't know, should we just skip to the third one?
Yeah.
Okay. So, let's jump straight to the third one. Here we'll do intersection, or subtraction.
Subtract.
Here we'll do, oh, that's still that. Read it right, over here. So now, what is, first off, V minus W just gives us what?
2 to 3.
Let's just write out what exactly that is.
No.
So
Oh,
F
0
inverse
to 1.
of V minus W, we're taking this and we're subtracting all these points, leaves me 0 to 1, not including 1, right?
Yeah.
And then
Yeah.
So F inverse of that is what?
Negative 1 to 1, but you don't include
Perfect.
either of them.
Negative 1 to 1, not inclusive. These
Where-
are all the numbers such that when you square them, you get something in there. Right?
Mm-hmm.
Now, let's look at this. Should have kept my number line up, right? Shoot. We had negative square root of 3, we had square root of 2, negative, we had negative 1, we had 0, we had 1, we had square root of 2, and we had square root of 3. Okay, W was everything from here to here, unioned with everything from here to here, and V, F inverse of V, I mean, was this. Right?
Mm-hmm.
So if I have this set, and I subtract away all these points, I'm left with these points. Right?
Yeah.
Left with these points in between, which is just negative 1 to 1, not including negative 1, not including 1. Good?
Yeah.
Okay. Okay. So feel like we got those? Do we want to do proofs of any of those, or do you like it?
like
You like it? Okay. Yeah, so some more definitions. Shoot, we have to erase these. So the first, now we're just basically going to define one-to-one, onto, and bijection. So remember that a function was only a function if it mapped every x to one and only one y, right? A function is going to be onto if every y is paired with one and only one x.
right.
So another way that we say that is if the inverse of a function is, well, we didn't talk about the inverse, it's just flipping elements, which we probably should have. But let's get intuition for what the inverse is really quick. So if I say f is equal to 1 goes to 2, 2 goes to 2. Really simple function. This is going from 1, 2 to 1, 2. She's going from 1, 2 to 1, 2. Good? So I have f from here to here. Here's my x, here's my y. So f is from x to y, and it's just this function. Then f inverse is 2, 1, 2, 2. You just flip all the elements around. That's what the inverse is. Now notice that the inverse is not necessarily a function. Here we had a function. Everything in here, every left-hand element mapped to one and only one right-hand element. When we flipped it around, every left-hand element did not map to one and only one right-hand element. So when you have a function, just because you take its inverse doesn't necessarily mean you have a function. The problem was we had two x's going to the same y. If both those x's went to different y's, then when we flipped it around, we would still have a function.
Okay.
Right?
And that's called an onto.
So if f from x to y is 1 to 1, this isn't a function, this is just 1 to 1. I don't like writing f for 1 to 1, I'm just going to do 1, 1 like that from here on out. If f of x is a 1 to 1 function, then f inverse from y, oh, it's not going to be from y to x. Shoot. It's only true if it's bijection.
What?
Because he only introduces these functions from a set to a set, it makes it hard to talk about these things. Sugar, I can't say that.
And I really like how this guy talks.
Alright, sorry. Sorry. Forget all that. We'll just have to take this definition and work with it directly. Why aren't we able to do it like you think I should? Remember in discrete math, we have a different definition for a function.
Yeah.
In discrete math, a function is a relation such that every left-hand element is paired to one and only one right-hand element. In this class, anytime we talk about a function, we're talking about a function from a set to a set. We never just talk about a function. We always talk about a function from a set to a set. In discrete math, we can just talk about functions, and we can talk about functions from sets to sets. In this class, we only talk about functions from sets to sets. Same thing with relations. In discrete math, what's a relation? It's just a set of word pairs. In this class, what's a relation? It's a subset of a set cross a set.
Yeah.
It's a relation from a set to a set. We also had that in discrete math. We had relations from sets to sets, but we also just had relations. So in this class, we're always restricting ourselves to talk about relations from sets to sets, or functions from sets to sets, and not just functions in general, and not just relations in general. Which makes me realize I forgot to mention a note I did over here. Made this note in discrete math, I think, but we'll make the note here, just in case. When we're talking about functions from a set to a set, we often call them maps. So since we sometimes talk about just functions out in the blue as functions by themselves, and since we sometimes talk about functions from a set to a set, to help us remember that the type of function we're talking about is from a set to a set, we often call it a map. Yeah, I know. I forgot to cover that, which is why I'm bringing it up now, but not pointing there, because that's not on the camera.
I actually read that though.
So, I might accidentally say we have a map from x to y. I'm just talking about function. And it's common vocabulary, and it's on purpose that it has a different name. That's not to be confusing, it's to help clarify. We're not talking about functions just out in the wild on their little lonesome. We're always talking about function from a set to a set. That's what map is. Make sense?
Yeah.
Okay. Now in all that, we got to get back to what it means to be one-to-one function. So let's go back to a function. Let's go back. I'm going to give you my favorite way of talking about a function. So I say a relation f is a relation f from, we'll follow the author does, x to y, is a function if and only if x equal if and only if, we'll say for all x, y in the domain, x equal to y implies f of x is equal to f of y. That's how I like to think about function. If I grab, anytime I grab two things out of the domain that happen to be the same thing, they better map to the same thing. I can't have two equal things mapping to different values, otherwise it's not a function.
That's what this guy said.
I can't have one going to 3 and one going to 4. So if my inputs are the same, my outputs better be the same. That's how I like to think about functions. Now what does it mean to be a one-to-one function? It's a one-to-one function if and only if for all x, y in big X, f of x equal to f of y implies x is equal to y. If the outputs being the same implies they came from the same place, then the function is one-to-one. Does that make sense?
Yeah.
It's a function if anytime I have the same inputs, I have the same outputs. It's a one-to-one function if anytime I have the same outputs, they came from the same input.
I have a question. Is your definition of a function the same as the one the author uses?
The one
In this book? Because it seems like
the author uses is written out this way. By x, y, be says that a function f from x to y is a relation from x to y such that for all x there exists one and only one y such that x is related to y.
right, that definition requires that you use all of x. I'm saying your definition doesn't really require that you use all of x, does it?
You are right. If and only if for all x and y, yep, you're right. I'm not adding that on there because, well, yeah, that's a good point. So this has a shortcoming. This isn't technically a good definition. Why? Because I'm not using all of x. So I need to say for all x in x, f of x is defined or something like that, and this thing. But the reason I like pointing this out is to help you understand one-to-one. This definition works when we're not talking about from a set to a set, right? That works for a generic definition of a function, so that's why I have it in my head wrong.
This guy did the same.
Okay, so that's a function, that's a one-to-one function. What's an on-to function? So, if we have some function from x to y, we call the function onto if the image of x is equal to all of y.
Right.
Let's give you an example of a function that's not onto. This. Using this function, what is f of all the real numbers? It's equal to all the numbers from 0 to infinity. It's not equal to all the real numbers. It's equal to some of the real numbers. This is a subset of that.
It's not.
Let's give you an example of a function that's onto. F of x equals x cubed. Okay, now this is onto, because now f of r is all of r.
Right, but it's not, for your square, it's not one-to-one.
It doesn't have to be one-to-one. It's completely separate.
Right.
A one-to-one function satisfies this condition.
Right.
An onto function satisfies this condition. And then finally we have the notion of a bijection. A bijection is a function that's one-to-one and onto. If it satisfies this property and this property, it's a bijection. F cubed, or f of x is equal to x cubed, this is a bijection.
The line. That makes.
F of x equals x is also a bijection. A line through the origin. Any line you can draw, f of x is equal to mx plus b, where m and b are just constants, is always a bijection.
Could you give us an example of a function that's onto but not one-to-one?
A function that is onto but not one-to-one.
Yeah, negative x squared. No, y.
It's on 2, so it has to use all of r, but it's not 1 to 1, so it has to have repeating value. Oh,
X squared.
tangent function. Tangent function maps everything, so it's on 2, but it's not 1 to 1 because it repeats over and over and over again. Do you guys know what the tangent function looks like?
Yeah,
No.
it's a whole bunch
So
of
you,
upside
those of
down
you who haven't
shapes.
taken trig before, let's draw it out real quick. What does it look like roughly? Here's 0, here's pi halves, here's negative pi halves, has an asymptote, and then if you keep going all the way over here, there's 3 pi halves, and if you keep going over here, here's negative 3 pi halves. Okay, what does it look like? It goes and then through there, and then up. So it maps everything from negative pi halves to pi halves in just this interval. It maps to every real number. Pick any real number you want, negative 10 trillion. There is a point, namely right here, such that the tangent at that point is negative 10 trillion.
Okay.
And it does this over and over again. So if I count, it repeats the exact same pattern over here. So it's not 1 to 1 because the tangent at 0 is 0, and the tangent at pi, negative pi, is 0, and it does the same thing over here again, and the tangent at pi is 0. So it keeps giving, for different inputs, it gives the same output. So it's not 1 to 1. It is on 2 though.
Because it covers the whole.
Yeah.
Interesting.
Okay, so there's an example of one that's, yeah, it's helpful with pet trig. If we can find a good textbook, we can do that over the summer.
Oh, I'm so down.
That kind of just turned my rails into for a while.
What?
I just forgot about that stuff.
Trig? Yeah. Okay. So that's bijection. So from the top, how do I know it's a function?
If it has a unique y value for every x.
Yeah, every x is mapped to one and only one y. How do I know it's 1 to 1?
If you flip it, y's can map to x's.
And X is
That's one way to say it, but that's not the way we're going to use it. The way we're going to use it is this way.
The image of two aligned
If the
x
image of
inputs.
2 points is the same, then they came from the same point. Or every image point is mapped to one and only one pre-image point. And then what's a bijection? Or sorry, what's on 2?
When the whole range is used.
Yeah, when the image of our domain
Maps.
is equal to our codomain. He calls it range, which he shouldn't, because that's not how students are used to using range. Students are used to using range for the image, not for the codomain. Okay, that handles definitions with functions. Then we just have a bunch of examples. No,
We
we
have
don't.
more
We
definitions.
have a lot more definitions.
With 7 more.
Oh, terminology that we might come across. When a function is 1 to 1, that is the same thing as, I don't even remember which is which. That is also called injective. And when a function is on 2, that is also called surjective. And then when it's both, it's called bijective.
Mm-hmm.
So 1 to 1 and injective are the same. On 2 and surjective are the same. And then if it's both, it's called bijective. Just other terminology that you Why we have both those, I don't know. I'm not sure where the injective and the surjective come from, but they're a lot closer to the bijective. Let's see. Oh, showing that a function is. What is he showing here? Showing that it's 1-to-1. And showing that it's onto. And showing that it's a bijection.
You literally just write this whole book in your book.
I write condensed versions of it.
They already have pretty condensed right here. You do every example.
Should we? Yeah, and then I sometimes add my own examples if I feel like you didn't cover it enough.
Or
Like
examples of you.
we did with the stuff right here. I went a lot more into this example than he does. So I just consume it however I feel is best and then put it on my paper as teaching notes, however I want to teach it. Okay, so next we're going to prove that some functions are are bijective, so that they have both those properties. But I'm wondering, should we stop now and continue next week? Because that could be a good pickup point
Yeah.
to reintroduce the material, start by proving something has these properties, and that's a good way to reintroduce them.
Yeah.
So, okay, so yeah, we'll call it there. So, for those of you following the book, the next thing we're going to be going over is example 0.12. So, that will be a proof using these if you care. Alright, yeah, we'll call it there. Pick it up next week.